Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo.
All right, good morning, everybody. Can you hear me okay?
Yes, I can.
All right. All right. Well, thank you all for joining us for another TESCO Tuesday. We are starting now because it is 11 o'clock. So give me 1 second here as I get everything going. All right. All right. Okay. So today, CT testing, theory and practice. We are going to be covering field testing next week. We'll talk a little bit more about it. But today we are going to focus on CT testing, theory and practice. So what we're going to cover, we are going to cover what CTs and PTs are and why we use them. We're going to talk about reading and interpreting a transformer faceplate, as well as why we test the CTs and PTs. We're going to talk a little bit about shop testing today, why you shop test new transformers, why you use manufacturers' tests, how utilities use these tests. We'll talk a little bit about magnetization and demagnetization. Again, we'll cover more about that next week. And we will touch on the types of field tests that we'll cover in greater depth, like I said, in next week's TESCO Tuesday. All right. And I am going to try very hard to not let you go early. I've got you for a whole hour. All right. And we do have a video that the team put together at the end for Halloween, which hopefully you'll enjoy at the very end. It takes about 2 minutes. All right. So first of all, self-contained versus transformer rated. Obviously, there's lots of different forms out there. There's lots of different services out there. We use self-contained for many of them. We use transformer rated for even more of them. While there are typically only 10 or 11% of your population is transformer rated services, they do come in a lot more flavors than the self-contained do. All right. The real key, self-contained is direct, transformer rated is indirect. I realize we've covered this in some of the earlier sessions. Again, these sessions are designed to really mimic a meter school, so that if you attend each of them, you should feel like you've gone through an intermediate to an advanced metering school. And so we'll touch base a little bit on things that we've covered in previous presentations. We'll cover everything that we're covering here, and then we will at least preview some of the things that we will be covering in subsequent ones. If you guys are interested, I believe that Andy and Steph have recorded all of the previous ones so that you can listen to them at your convenience. All right, self-contained. Primarily, this is our residential, 1S, 2S, 12S. Relatively low current. So for example, this house right now is drawing 100 amps. That's actually quite a bit. Most of our homes, we're typically pulling a couple of amps, 10 amps, 20 amps, 30 amps. You plug in your electric car, you might be pulling 48 amps. So actually 100 amps means you've got all the ACs going, you're pulling a pretty good load. Most of our meters are 200 amps or class 200. The meter is right in line. If you remove the meter, you're basically disconnecting the power, unless you put in some jumpers. All right. Now, what's the difference? Transformer rated, 9S, for example, we got 600 amps going into the factory here. You can't put the meter right in line because the meter is not designed to handle 600 amps. All right. So what we use is we use CTs, and sometimes we also use PTs. So what exactly is a CT? We call them CTs, current transformers. They are actually a type of instrument transformer. An instrument transformer is a transformer that has a rated accuracy of at least 0.3% accuracy or better. When I say 0.3%, I mean that you're getting 99.7% of the anticipated ratio or better. All right, that's your definition of an instrument transformer. what we do with these instrument transformers, and similarly on a PT, we're stepping down the voltage. So what we're doing is we're taking those 600 amps and we're stepping it down to something that we can handle inside the meter. All right, which means that the meter is not in the direct service line. So we are isolating the metering part of the service from the service to the building, which is pretty helpful because you certainly don't want to be taking your commercial industrial accounts down because you're changing the meter. And it also wouldn't be very safe for the meter tech. All right. So you can use CTs and you can use PTs. You can use them in a variety of different ways, but primarily we use them for our commercial and industrial accounts to step down the current and step down the voltage as we need to so that we can actually meter it. All right. Let's talk a little bit about them. How does a CT work? It's pretty basic. All right. The number of windings, that's your ratio. So if I've got a 400 to 5, that's a ratio of 80 to 1. That means I got one primary and I got 80 of these secondaries. All right. And it's a direct correlation between current 1 and current 2. In a perfect world, there are no losses. Okay. So I2, the secondary current, is equal to I1 times the ratio of the coils, 1 to 80 in this case. Okay. That would give us a 400 to 5 CT. I know that we've talked about it before, but I'll say it again. The reason that we use everything to 5, 200 to 5, 400 to 5, 1,000 to 5, 2,000 to 5, 6,000 to 5, 8,000 to 5, the reason we do everything to 5 is that the very first commercial industrial meter that was developed back in the late 1890s, I believe it was 1898, by Westinghouse, it was most accurate at 5 amps. So everybody tried to set their service so that they were getting 400 amps to 5, 200 amps to 5, 50 amps to 5, so that that meter would provide the greatest possible accuracy. Back in those days, the meters were not typically 0.3%. They were not that accurate. They were not that consistently made. They were basically all made somewhat by hand. So given that, everybody tried to go to 5 amps. We're well past that. Our CTs are much better than that. They are extremely accurate. We don't have to worry about going to 5 amps. The sweet spot of the meter is no longer 5 amps, but we're a very conservative industry, so we still do everything to 5. In Europe, you can find what they call unity transformers, which are a ratio to 1. So you would actually see an 80 to 1 transformer over there. Possibly you will also see 400 to 5s. The best reason to go to unity is that it makes the guys in the billing department often get their math wrong. You tell them it's an 800 to 5 and they say, oh, so what's my ratio there? Is that a multiplier of 100? No, it's 800 to 5. Just divide 800 to 5. That's 160 as your multiplier. Oh, okay. There are a lot of billing errors that have come up over the years strictly as a result of somebody doing that division incorrectly, getting the wrong multiplier after dividing 400 divided by 5 or 800 divided by 5 or 1,000 divided by 5. You'd be surprised, or maybe you wouldn't. Okay, so we have our transformer, and here's our primary, here's our secondaries. In a perfect world, I have no losses whatsoever, and there's an engineering model of an ideal world with no losses. However, we don't live in an ideal world. I know, shocking to some of you, but it's true. We don't really live in an ideal world. Every transformer requires a certain amount of current to begin working. We call it an exciting impedance. It's not really overly exciting, but it is to that transformer. So it takes a certain amount of that primary energy to actually get the transformer working. Because of that, transformers are always something less than 100% accurate. Not much. It's very, very small. It can be measured, but it is very, very small in terms of its loss. There is always something, though. So when we are billing our customer, we know that we're actually always billing them just less than 100% of the energy being delivered, all right, which is typically what our industry likes to do. Same thing with your meters. When you receive your meters, all of the meter manufacturers have traditionally calibrated up to 100%, which means the overwhelming majority of them come in at just under 100%. We always want to make sure that we are erring on the customer side instead of on the utility side. All right. So again, pretty simple. Primary, secondaries, that's your ratio. You do have a certain amount of loss there when you have a transformer. Okay. So here's kind of a typical operation. You've got a 400 to 5 transformer, and typically you would have 3 of these in the line, one for each phase going into, it doesn't go directly into our meter, it actually goes through, traditionally it typically goes through a test switch. The reason you have the test switch is that you can isolate very quickly the whole metering circuit, and you can interface all of your test equipment when you're going to test it in the field. And again, we'll see more about that next week. All right, so here's a standard, here's your typical application. 400 to 5, 400 to 5, 400 to 5. Our test switch, everybody's test switch is configured a little bit differently. Some people like to have all the potentials together. Some people like to have the 2 currents and a potential in a block. Some people want dividers everywhere. Some people want multicolored. Some want plated, unplated. It makes really no difference. The test switch itself is actually a really clever device that allows you to very safely bypass and reconnect the metering circuit to the surface. We talked about that. We had a whole presentation on them last week, so I won't bore you too much, but test switches have been around for a very long time. We celebrated their 100th anniversary this summer in August. That's when the patent was awarded. They were actually in service a few years before that and actively used by many utilities. It's a knife blade switch. Knife blade switches went out of vogue in the 1920s. But it's a very safe, very clever design, and there's a massive infrastructure. If you understand how to utilize the test switches in your service territory, you understand your color coding and how you use them, whether you use reverse potentials or not, you can operate those test switches very safely, and you can work with those commercial industrial accounts very safely. You can test them. You can do things without interfering with the customer or blowing up a transformer. Or doing anything else catastrophic. So utilities have maintained that infrastructure, and we continue using a knife blade switch. Even though knife blade switches are out of vogue for almost 100 years, we continue to use them because it's a safe and secure application in this case. All right, let's talk a little bit about the faceplates. So everybody's probably seen a faceplate on a transformer, but you may or may not have paid a whole lot of attention to it. It is a very important piece of the puzzle. So first of all, here's we picked one that we had downstairs. This is an Alstom transformer. There's a number of very good transformer manufacturers. In general, in our industry, every manufacturer, unfortunately, including even our competitors, are very good manufacturers. If you're in this industry, utilities expect the best. There's really no tolerance in our industry for anything less than the best. So if anybody's been around for a while, there is a reason, and that's because what they produce and what they supply to the industry is a good quality product. All right. So this is just one of several current transformer companies. In this particular case, I've picked one that is what we call a dual ratio. These were very popular back in the 1990s. They came into vogue, and they allowed the utilities at the time to reduce the number of SKUs that they had, because depending on whether you connected X1 and X3 or X2 and X3, you could create a ratio of 300 to 5 or 150 to 5. Now we are moving to extended range transformers, which kind of accomplishes the same purpose in that you have a fewer SKUs in stock to cover a much wider range of applications. The knock against the dual ratio is the dual ratio, first of all, didn't change anything in the accuracy, whereas the extended range actually not only improved the overall range that the transformer would operate at, but it also improved the lower end of that range dramatically, which we'll talk about in a few minutes. The bigger problem, though, with the dual ratios is that if you have one of these transformers out there, it's a perfectly good transformer. If we took it back into the shop and did a really good accuracy test on it, it would probably be approximately as good as the day it was manufactured. Very good transformer. But if you have these out on your system, I guarantee you that somewhere on your system, there's a place where billing thinks you hooked up the 300 to 5, and it's really hooked up as a 150 to 5. And the opposite is true, where billing thinks it's a 150 and it's actually a 300. So think about that. In the one case where billing thinks it's a 150 and you hooked it up as a 300, we're billing the customer 50% of their usage. If you flipped it around and billing thinks it's a 300, but you hooked it up as a 150, we're billing the customer double what they should be billed. Neither one is a good thing. Both end up very ugly with very upset customers. All right. And if we were actually, you would think that the customer would be very happy. Okay. We have a question in the chat. I'll come back to it in just 1 second. You would think that the customer would be very happy to learn that he was being double billed and he's going to get a big refund. We had a customer, we had a utility, one of our customers who discovered this problem several years later. They were doing a field audit, discovered they'd been billing the customer twice. What they got back instead, after sending a $7 million check to the customer, they got back a lawsuit. And the lawsuit said, we are suing you because how do we know it didn't happen for a longer period than what you said? And even though by code, you're only supposed to go back so many years, we think you owe us for the years before that as well. And what about all the lost opportunity that my client had because they could have taken that money and invested in new products, plant expansions, and there is a tremendous amount of lost opportunity costs. So that one didn't end very well. On the other hand, we also had a customer who discovered several years later that they had underbilled the customer by 2/3. They had a CT that was wired backwards. In that particular case, they came back, they didn't backcharge the customer anything, they apologized profusely, they corrected the service, and within 6 months, the customer and 100 jobs were gone because they could not afford triple the energy bill because energy was a major component of their manufacturing cost. All right, they were an extruder and they couldn't handle triple the bill. The utility acknowledged it was their issue. Nobody had tampered with the service. It had been that way since the building was built 8 years ago or something like that. But that customer had already set all their pricing, all their wages. They couldn't come back to their customers and significantly increase their pricing. It wouldn't have been triple, but they would have had to, they said it was an increase of almost 80% over their established pricing. They had contracts, long-term contracts, they couldn't come back, and the company went out of business. Now you could argue, would they have made it in the first place if they'd been getting the right energy bill? They would have at least had a chance. They could have priced it correctly from the beginning. So this is your ratio. It's on there. If you have dual ratio transformers, I'd strongly suggest thinking about them or at least checking them on a very regular basis. Even though they shouldn't change once they've been installed, you never know. Customers learn all kinds of wonderful things on the internet, right? Okay, so that's the first thing that's on the faceplate. That is the ratio. All right. Somebody asked a question. What type of current transformers are best to use? Donut or bar types? There is no better or worse. I personally like the bar types better. The donut types are a little easier to install, I believe. But actually the wires going through your donut transformers, as you get to the larger and larger ratios, like a 2,000, 4,000, 5,000, 8,000 to 5, the way that the service goes through that donut is important to the accuracy of that transformer. This 400 to 5 transformer, this is a donut type, so the wire passes directly through. In a perfect world, you pass that wire directly through the center of that circle to give you the maximum accuracy. But the fact is, if you measure the accuracy of this and you measure the accuracy with the wire up here, down here, up here, or in the middle, it is not appreciable. It's only with the best shop equipment could you even really measure it. It could be measured, but it's very infinitesimal. It would never change the accuracy of the customer's, in no significant way would it ever factor into the customer's bill. And the fact of the matter is, if this transformer with it running perfectly through the center was 300.9999654, and with it on the edge was 3.999428, in the end, you're just going to use 400 to 5. I have never seen a utility that took the actual accuracy of the transformer and used that as their multiplier. Everybody simply takes, it's a 400 to 5, I'm using 80 as my multiplier, period, end of story. All right, so on the higher ones, I definitely prefer the bar. In general, I prefer the bar, but that's just a personal choice. I could put a whole panel of 40-year utility veterans, and it could be pretty equal between donut and bar. It's just personal choice. What works best for your utility, use either one. They are both just as good for the applications, especially if you're not talking about 2,000, 4,000, 5,000 to 5s, whatever works easiest for you. Okay, so again, all this means is when 400 amps are applied on the primary, you get 5 amps out on the secondary. All right, the next one. On every faceplate, it's called a rating factor. In this particular case, it's relatively low, 1.5. A lot of times you'll see a rating factor of up to 4.0. Rating factor is a bit of a misnomer. Its true name is thermal rating factor, okay? Thermal rating factor. What the heck does that mean? That means that on this particular transformer, if I've hooked it up as a 300 to 5, I can very safely put 450 amps through the primary and have no problem whatsoever. If I start to go above 450, I will start to overheat the transformer. What's the problem in that? Well, what is a transformer? I basically got a whole bunch of turns in here, okay? In this case, I got 80 of them. We know that. I got one primary that's going to be coming through here. Well, I got 80 turns, and what are they encased in? They're encased in traditionally some sort of butyl rubber, all right, or some sort of hard encasement, all right, that holds those windings, all right? As long as I don't catastrophically fail the transformer, that transformer is going to be just as accurate in 30 years as it is today. Well, how would I catastrophically fail that transformer? One way is to overheat it. As I overheat it, those coils want to do what? They want to expand. Well, there is no way for them to expand because they're fully potted, all right? There's no way that they can expand. All right, now, as they expand, if I really overheat this, eventually what it's going to do is it's going to crack that potting. Once the insulation begins to break down, that potting begins to break down, now I could have a turn-to-turn short in that transformer, and I will have a problem. That transformer will fail. So the thermal rating factor is important. That tells me how high I can use. We're going to talk about the accuracy in just a second, but what most people don't realize is if this is a 400 to 5 transformer, you would expect that its accuracy is going to be best up to that rating, 400 amps. In fact, that's not the case. It's actually best from 400 amps up to the limit of its thermal rating factor. So in this particular case, this 300 to 5 transformer, it will measure the best. It will measure at its rated accuracy, at its faceplate accuracy, between 300 and 450 amps. If I put less than 300 amps on the primary, I will get less than the rated accuracy on this transformer. And we'll talk about that more in a couple of slides. All right, but it's a very important thing to remember, and many people are not aware of that, okay? All right, so that's our thermal rating factor. Now, when we talk about a thermal rating factor, there is an ambient, and that's in degrees C. All right, so there is an ambient, which is our standard temperature. So does this thermal rating factor change if it's colder? Yes. If it's colder, it will change a little bit. If it's hotter, it will change a little bit. This theoretically could go up a little bit or down a little bit. But for all intents and purposes, with a thermal rating factor of 4.0, I can take this 400 to 5 CT and I can bring it up to 1600 amps. Okay. All right. So the accuracy is actually an accuracy and a burden rating. So in this particular case, don't know if you can see it, but it says it's 0.3% between these burdens, starting at 0.1 and going up. Okay, it means if I get too much of a burden, I'm going to lose accuracy. All right, it says 0.3% accuracy. So I'm going to come back to that slide in just a second. I want to come down to here. So this is the accuracy of that transformer. I did a whole bunch of readings at 0 burden. I put in 400 amps, for example, and I got 5.000 out. I read it to 4 significant digits, and I got that. At 0.1, I got 4.999, 0.2, 4.995, 0.5, 4.99. In this particular case, this transformer that we were working on, its faceplate said 0.3 at a burden of 0.1, 0.2, and 0.5. All right. After that, its accuracy is going to deteriorate. The manufacturer doesn't necessarily tell you how it will deteriorate, certainly not on the faceplate, but you can get these graphs from the manufacturer, and you can get this data from the manufacturer. Remember I said it's 0.3% right there. So that means 99.7, all right? So when I drop below 0.5, okay, I start to get I start to drop off, and you can see it right here, but I don't really go out of accuracy for a little while. But notice what happens once I start putting on 2 ohms, 4 ohms, and 8 ohms worth of burden. The accuracy drops way off, way off, all right? And again, we'll come back to that in just a little bit. So how do you test in the shop? I'm going to digress for just a second here. These are pieces of laboratory equipment. These are made by Canop, and Canop is part of TESCO. So I'm not trying to give you a shameless plug, but as far as we know, there is no more accurate laboratory equipment for testing your transformers. These have been around a long time. Canop started in 1928. Even the designs have been around for a long time, but they are still state of the art in terms of accuracy. Why? Because it's a really tiny market. Only electric utilities are interested in this level of accuracy, and the manufacturers of the transformers. And really only the largest of the investor-owned utilities have their own equipment. Most of the rest of us rely upon the manufacturers who also use this equipment. This right here is a voltage test system, and it's a little easier to see because the precision transformer is right here and the loading transformer is right here. All right. These precision transformers are exceptionally accurate. This particular one goes up to 14,400. We also make one that goes up to 36,600 because that's the limit of what our metering customers really need. And all you're really doing is you're taking your transformer under test, which might be here, you're hooking it up, and the loading transformer is feeding the precision and your transformer under test, and you're comparing what the precision is outputting and what your transformer under test is outputting. Compare the two, that's your accuracy, okay? Pretty basic, all right? Same thing in your, this is a KCTS, this is your current transformer test system. The transformer under test hooks up right over here, and inside of here is a precision transformer and a loading transformer. That particular precision transformer has a feature that allows you to test it against itself every day, just to do a sanity check to make sure that everything is still working correctly. So it basically splits in two, measures against itself, and should always come back 100% accurate. All right, so it's called a self-test. Once again, this is a highly precise transformer. Both of these are directly, we have ones in our lab that are directly traceable back to our international standard. And as far as we know, as I said, there's nothing more accurate than either of these. So why would you use these? Well, you would use it on your new transformers to do a check of your new transformers. You can either do a selective test or a statistical test of a new batch of transformers, or our recommendation is a full test. Why do we recommend a test of all of them? Because we suggest that you test all of your instrument transformers and all of your transformer rated meters in the shop before putting them out into the field. Why? Because that's where all your money is. These are your largest customers, okay? You don't know if the 800 to 5 customer that you're gonna put a CT on is gonna be giving you $20,000 a month in revenue or $2 million worth of month, $2 million per month in revenue, all right? These are going on your very largest accounts, and you wanna make sure, you wanna do everything in your power to make sure that they are accurate. Do manufacturers make mistakes? Yes. We make mistakes. All manufacturers make mistakes. We don't make many. You don't allow us to make many. And what's more important is if we make one, we got to make right on it immediately. Well, if you make a mistake on marking a transformer, that can be a big problem, all right? If you test it, you can catch that problem. Does it happen often? No, it doesn't. How often does it need to happen to justify 100% testing? Well, if it happens one time on $1 million a month customer, that may justify your testing for a whole lot of decades. All right. The manufacturers also do 100% testing, but again, a marking could be done incorrectly afterwards or before. Use transformers. Why would use transformers? Why would you want to test used transformers? The only reason you would want to test used transformers is if for some reason there is some sort of billing dispute, or if you're going to be returning a transformer to service. Is a 15 or 20-year-old transformer still good? Probably, yeah. There's no moving parts. As long as you haven't overheated it, as long as you haven't put too much current through it, as long as it was manufactured properly, if it's been working for the last 15, good chance it's going to work for at least another 15 and probably longer than that. So if you wanted to reuse a transformer, absolutely check them out in your shop, test them. You can probably put them back out there. There are reasons why you might not only because there are better transformers available now than there were 20 years ago. And by that, I mean the extended range transformers. Okay, so typical tests. What are we gonna test when we test a transformer? Well, we'll do an accuracy test. That's really just a ratio test, all right? And that's gonna give us our accuracy class determination. We're going to do a burden test because we want to see how that transformer operates over a variety of burdens. We're going to do a polarity check. Well, what's a polarity check? If you remember over here, see that little white dot there? That marks the polarity. That tells you how that transformer should be set up, all right? If I have 3 transformers in a box, all 3 transformers should be wired the same way with the polarity marking pointing the same way. If one of them is wired backwards, it will cancel out a second one. And if it's perfectly balanced, I will lose 2/3 of the bill. Okay. I have seen batches of transformers where the polarity marking is incorrect. It's actually on the back. Is that a problem? If you use those transformers together, it's never going to be a problem because they're all going to be wired the same. And backwards or frontwards, the transformers doesn't care. It's going to work. Remember, it only cares about one primary and the number of turns. All right. However, if I have a whole batch of transformers that were marked incorrectly and I didn't reject them, then if I ever used 1 or 2 of them with a transformer or 2 transformers from another batch, I would have a problem. So again, it happens very rarely, but I've actually seen it 3 times now. But I get to see probably more instrument transformers maybe than most folks. So it's very rare, but it does happen. So checking the polarity is also important. And then demagnetizing the CT. You want to demagnetize your CT anytime you do any work in the field and before you put it out in the field. Well, why you would wonder, why do I need to do that before I put it out in the field? You want to do that because CTs can come from the manufacturer magnetized. If you're not checking them, if you're not doing 100% check, you can put that magnetized CT out in the field and you may not know it until the first time you do a field check on it, which may or may not be 90 days after, or maybe it's a couple of years after, or if it's a small enough service, maybe you never do it. And if you do that, you'll never notice that there was a problem because it was, quote, always that way. The bill never changed. There was no radical difference in the way the service performed and was metered. All right. So demagnetizing them on the way out, if no other reason, that should give you a reason to test all your transformers before they head out the door. Okay. The burden range. All right. So why are transformers given an accuracy reading with a burden? Because theoretically, there should be no burden. But once again, we don't work in a theoretical world. We don't work in an ideal world. There are burdens. How do we create a burden on a setup? Well, the amount of wire that we have between the transformers, the test switch, the meter, that length of wire and diameter of wire, that puts a certain burden on the service, okay? You want to ideally always put your transformers as close to your pre-wired box, as close to your test switch and meter socket as possible. Sometimes that is just not logistically possible for lots of good and bad reasons. I'm sure if you've been out in the field for any length of time, you have seen CT boxes that are more than a couple of feet away from the meter and the test switch. The meter and the test switch, I have virtually always seen them in the same box. I'm not sure I've ever seen them not in the same box, although I have seen some that didn't have a test switch, which made doing field checks very difficult. But occasionally you'll see them more than a few feet away. Most utilities will say that they give you a range. Once you go beyond that range, you have to go up in the size of wire that you use. You need a thicker wire. Why is that? Because that thicker wire has a lower resistance, a lower burden. So, oh, you got to go 15 feet. Sorry, you got to go up. And that makes that wire a lot more expensive for the utility because there's a lot more of it and it's a much thicker wire. And it's a lot harder to work with. If you ever tried doing that, it's a pain in the butt. So you'd rather not do that. You want to keep them together. The other thing that happens is you'll get loose connections over time. Maybe there's vibration inherent in that area. Maybe there's a train or buses going by, or the equipment in the plant is constantly vibrating. Or you get corrosion. So corrosion, loose wires, maybe strands are beginning to break. All of these things can start to affect the accuracy and can change the burden. All right. We're going to talk next week about admittance testing and the ability to take effectively a snapshot of that service and comparing it to the last time you were out there to check that service and see if anything's gone on. And one of the things that will change from year to year, decade to decade, is the amount of burden that the transformer is actually seeing. Okay. And again, just corrosion. So one of the things that you can do when you go out to an instrument rated service is, as you're doing your full site inspection, clean it up, get rid of all the corrosion, and tighten everything down. Just doing that may improve your metering accuracy as much as a couple of percent. And that's huge. That's absolutely huge, especially when you figure the meter that's in there is probably spec to like 0.5% accuracy. Just you cleaning up that service, taking a wire brush and tightening everything up can improve the accuracy sometimes by a couple of percent. All right, so this burden test is important because what we want to understand is that, okay, I can take some burden here. I can take some burden and really not see any significant loss of accuracy. Okay, you can see, between 0 and 0.5, I really didn't see a very significant loss at all. I'm well within my specs. Okay, so we're doing okay here. That's why we're checking to burden. So doing a burden test is important to make sure that the transformer can handle a certain amount of burden. Now, this transformer, as good as it is, as perfect as it is, if I put too long a run of wire. I allow too much corrosion. I have some loose connections in there. I've got too much burden on the secondary, too much burden in that service. I'm just, no matter how good my meter, no matter how good my current transformer, it's just not going to give me the accuracy I expect. And you can see how badly it starts to fall off here once you get past this knee. It really starts to fall off quite badly. All right. These are our ANSI burden values. Okay, 0.1 to 8. There actually are some new ones that have been created in recent years for extended range transformers. We're not going to get into that tremendously here. Not overly important. But there are a series of ANSI burden values. If somebody does an ANSI test, typically you're running through all of those different values. So when you're doing that, like for example in the lab, there is a setting here where you can run through all of those different values. Okay. All right. Accuracy class. So this is, many of you may have seen something like this before. For some of you, maybe this is the first time, but this is the classic accuracy graph for transformers. This is not an extended range transformer. This is more your classic instrument transformer, 0.3% accuracy, again, at these burdens. Whenever you say an accuracy for a current transformer, you say at what burdens, okay? So here's our 0.3% accuracy. Remember, if this is a 400 to 5, it doesn't reach 0.3% until you are at that 400 amps. If it has a thermal rating factor of 4.0, it's going to maintain that accuracy all the way out to 1600 amps, or 4 times its rating. If this was a 200 amp to 5, 200 amps would be right here. It would be accurate at 200 amps all the way out to 800 amps. All right, everybody got that? Most people think it's good up to that. No, its accuracy starts at that. That's where it starts. So with a thermal rating factor of 4.0 or 1.5 or 2.0, it starts at 200 to 5, starts at 200. 400 to 5, it starts at 400. All right. Once you go beyond that, you may start to do damage to your transformer. So don't do that. All right. What happens when it goes below? Your accuracy goes in half. So if it was a 0.3, it's actually 0.6. Now, it's not actually a step function. It actually ramps up very sharply. But for all intents and purposes, and for every textbook or manual I've ever seen, they show this type of accuracy. But in the lab, it really goes like that. All right. So it gets half as accurate. Now, where on that faceplate, I'm going to go back up to my faceplate here. Where on this faceplate does it say that it is 0.6% accurate if you're at anything less than, say, 300 amps if I've hooked up the X1 and X3? So take a quick look at that if you can see it on your screen. And the answer is nowhere on this faceplate does it tell you that it goes to half the accuracy. That is just something that we are supposed to know. How do we know it? Because we're metermen. We're meter techs, we're meter engineers, we're metering supervisors, we're metering managers. We're just supposed to know that. Fun fact, there is no University of Metering, is there? Every single one of us on this call learned about metering when we started in a job in the meter service department or for a manufacturer servicing electric meter service departments for electric utilities. That's how you learn about metering. That's how you learn that, oh yeah, the faceplate says 0.3. But once you drop below the 400 amps on a 400 to 5 or the 300 amps on a 300 to 5, the accuracy goes in half. It goes to 0.6. That is a mistake that was made for many years by people when they sized CTs for a service. They'd say, oh, well, the customer is generally going to be using 100 to 200, and he could use as much as 800 amps. So they would throw an 800 to 5 CT. Bad idea. You really wanted to throw a 200 to 5 with a thermal rating factor of 4. That was the correct meter. All right. Now, so 0.6, just something that you have to know. You'll never see it on the faceplate. What's the other issue with the older transformers? this number right here, 10%. Do you know what happens to the accuracy once you drop to less than 10%? So on a 400 to 5, that would mean once you drop under 40 amps, you don't have any accuracy. You're basically getting no bill, okay? So what does that mean? If I have oversized my CTs, either by making the classic mistake that I just mentioned earlier, oh, he could go up to 800 amps, therefore we're going to put 800 to 5s. Big mistake made by people who didn't quite understand what the CT was and how you read the faceplate and what it actually means, all right? So if your boss made that mistake, try not to bring it up to him unless you can do it in a very nice way. It's not that people are stupid, it's just that people don't know. So they could have oversized the CTs right from the beginning. But a more prevalent issue is I only know of one utility that is just now beginning a program where they're actively going out and updating transformer rated sites with new transformers based on the new usage. The classic way of doing it, the way the overwhelming majority of installations in North America are set, I may have set the building I'm in, is a pretty old building. The CTs here may have been set 20, 30, 40, 50 or more years ago. Maybe the service, I know the service was last updated in 2004. So these transformers have maybe been here for 16 years, these instrument transformers on this building. Well, maybe 16 years ago, this building was used for heavy manufacturing. Lots of injection molders and stamping machines and a lot of heat-based processing, maybe an extruder or two. And it was using a lot of power. So we were bringing in maybe 1,600 amps. But now we've turned it all into offices and storage space. And now we're only using a couple of hundred amps. Well, if I oversize my CT, I'm operating at the very low end of the operating range. So I'm already getting half the accuracy that I thought I was getting, right? Because I'm operating in here. And on the nights and the weekends, I'm operating well under the 10%, which means on nights and weekends where I used to run a 4-shift operation, I'm now running 1-shift offices. Nights and weekends, I'm losing all of my energy measurement. I'm losing all of the revenue, okay? So that's the real knock against your classic transformer. All right, the extended ranges, all right, and I threw up, this is an older slide. The extended ranges do two things. First of all, they're more accurate, 0.15, okay? So if this is, again, I'll pick on a 400 to 5. If this was a 400 to 5 with a thermal rating factor of 4.0, from 400 up to 1600, it's actually good to 0.15. So it's double the accuracy of the normal one. Actually, I've got it right here. Sorry. Double the accuracy of the normal one. And when I get below the 10%, or below the 100%, it goes to 0.3, and then it works down to 5%. Well, since I put this slide together several years ago, the transformer manufacturers have improved on this, and I really need to update my slide. Many of the best transformers you can buy now are 0.15 all the way down, and this 5% is now arguably down to 1% or better. Some manufacturers claim they can go all the way down. We've never seen that in the lab. I'm not saying that they can't do it, but they're better than 1%. Why is 1% important? Well, shoot, even at a 400 to 5, the 5% was still 20 amps. Plenty of facilities will be drawing less than 20 amps off shift, okay? It's probably right at the limit, but if you go down to 1%, now you're talking about going down to 4 amps. There's almost no possibility that facility is ever going to get down to 4 amps. So basically, by using the newest instrument rated transformers, extended range instrument rated transformers, you effectively can guarantee that you will be correctly and accurately metering them all the way down to virtually zero, 4 amps, 8 amps, 2 amps, depending on the size of the transformers, all the way down to virtually zero. And your accuracy will maintain throughout the range, all the way up to the limit of the thermal rating factor. Now, some of those don't have a thermal rating factor as high as 4.0. Some of them are 1.0, some of them are 1.5, etc. But they are going to be, their faceplate is actually an honest faceplate where no matter what you put on it, that's the accuracy you're going to get. So again, the best ones are even better than what I've demonstrated here. Another fun fact, can you ever see a thermal rating factor of less than 1? Less than 1. So if I have 2, 3, or 4, it means that I can go to double, triple, quadruple. If I have less than 1, that means I can't even go up to what the faceplate says I can go up to. Well, what the heck is the point of that? Why don't I just be honest with you and tell you, no, I can't go up that high? In some of your very largest transformers, you can get a rating factor of less than 1. What does it mean? I've seen 6,000 to 5 and 8,000 to 5 current transformers that had rating factors, thermal rating factors of 0.8 and 0.9 and 0.7. The reason for that was they were installed on, obviously, very large services, which only expected to get to the very upper level of that once in a blue moon and for very short durations, which meant that the manufacturer managed to get all those windings into a package, but said, you know what? You can't put 6,000 amps on that and let it run for 2 days because it will break down. But if you're only going to put 6,000 amps on for half an hour or 15 minutes or less than an hour, it'll actually work just fine, but don't keep it on for an extended period. So for the very largest transformers, if you ever need to use something like that, you may actually see a thermal rating factor of less than 1. Don't be too afraid of it. Just understand what it means. It means you can't stay at 6,000 amps for an extended period, if that's what it happens to be, at 6,000 to 5. All right. How much can you go for if it's rated at 0.8 thermal rating factor, and it's a 6,000 to 5, means you can get up to 4,800 amps on the primary for an extended period without any problem. 4,800 amps or less, you're good. Start going above it, and you can't stay there for an extended period. All right. Okay, we already talked about the polarity check. So the white dot is important, and I see I'm running out of time. So I told you I wasn't going to keep you too extra long. Oh, and somebody else just made a comment here in the chat. The extended range is absolutely, so Matt, thank you for putting that in there. It absolutely allows you to go with far less inventory. So in Matt's case, he's using one transformer, is servicing everything up to 800 amps, which is great. All right. Demagnetization. So you can magnetize a CT for a variety of reasons. All right. And again, we'll talk a little bit more about it next week. Demagnetizing a CT can be done very easily. You basically, you slowly and you smoothly increase the secondary resistance, okay, until you saturate the transformer, and then you slowly and smoothly decrease the secondary resistance. When you're working on one of these units here, that's other than some of the older units, that's a standard feature in here that you have a demag on there. So it's very important when you're testing them in your shop, if you have a piece of equipment, you can do it. You can also purchase equipment that can actually just do the demagnetization. If you have field equipment, you can do a demag when you do your field testing, okay? Let's see here. Okay, so we talked about the manufacturer's test. Most utilities accept the manufacturer's test. Is there any risk to that? The only risk is that occasionally you'll see a mismarked CT, either with the wrong ratio or with the wrong polarity. So you could check that yourself, either by doing a check after it's installed. Some utilities do that, and they do a ratio and they check the polarity, make sure everything is good. We think it's a better practice to do it before, because you can also do the demag, but really it's up to you how you want to handle that. But the manufacturer's tests are good. You should always keep the manufacturer's data. It also gives you a baseline to check against, okay? You got your new transformers, your used transformers. Until people have extended ranges out there everywhere, I don't see a real need to be putting transformers back out in the field. The typical tests and checks that we would do in the shop, an actually test, which is again is the ratio test, the actually class determination, the burden test, polarity check, and DMAG in the, hold on one second here. DMAG and the CT. All right. Why do we think that it's a great idea to do 100% of your transformers and 100% of all transformer rated meters? Because again, this is where all the money is. All right. So a simple error, even if it's only 1 in 1,000, 1 in even 10,000. Yeah, if you only have a couple of hundred of these out on your service, or a couple of dozen out on your service, odds of you having this problem aren't very great. But just one problem can be a tremendous amount of money. So we really do encourage you to do it. Yes, we do make the equipment. We do it because we see a need. All right. And now I told you guys that I was going to do, we got 5 minutes left. Does anybody have any questions? Because in the 5 minutes that's left, I was going to show you a 2-minute video and then let you guys escape. But does anybody have any questions before we jump into that? All right, you can still ask the chats. I'll still see the chat while this is going. And I got to put it, hold on a second. Yep, I think so. Uh-oh, the video's not coming. Let's see, where's my, oh, shoot. The video's not coming. Oh, well, we'll show it again next week. Yeah. You know how to do it? Okay, we have a couple of questions here. Sorry, guys. We weren't able to test the video beforehand. We thought it was all going. Oh, well. All right. Okay, a couple of questions that we had. So you can also send, a few people sent their questions in earlier. Before the session began. So if you want to do that, if you look at next week's presentation or the week after and you've got some questions, send them in. All right, so the first one, is it really important to test every transformer before they are installed in the field? So yes, we think that it is for all the reasons that I just said a few seconds ago. We really think that that's a very important part of what you should be doing as a best practice, okay? What should we expect from the overall life of a CT? So the overall life of a CT is at least 30 years, and I have seen plenty that have lasted 40, 50, and 60. The real reason for changing them right now is the CTs you have out on a service may not be appropriate for that site any longer, okay? Again, the usage may have changed one way or the other. Most of them, the usage changed the wrong way. In other words, there used to be heavy usage, now there's light usage, and now I'm operating down in the, let me go up here. Now I'm operating down in the 10% range, and I'm not getting much of anything, or possibly nothing, okay? So your CT should actually be as accurate as it was 30 years ago. So if you get CTs in that are 20 years old, even 25 and even 30, if they test okay, you could put them back out there. But right now there are better choices with the extended range transformers. All right, one that just popped up in the chat. How often do you recommend testing transformer rated sites? So we recommend it's not just about the testing, but it's about a full site evaluation. My recommendation is every year. And on your very largest customers, you could even make a case for more than that. Why do things change? As we mentioned before, you can get just natural corrosion, things loosening up due to vibration at the site. Or sometimes electricians get in there and they're trying to get a new warehouse going. They're trying to do an expansion or a contraction or change something around. They can actually severely unbalance your load or screw up your load if you're not careful. And of course, there's always the possibility that that somebody could be tampering with the service. So our advice is once a year. If you can't do that, get your biggest ones on your greatest frequency, hopefully once a year, and your smaller ones at a lesser frequency. All right. Are extended range transformers really worth the extra money? Yes, they really are. They really are. We can't recommend them enough. We don't make them. We think they're a great idea. All right. Let's see. There's another question here in the chat. Like to know how easy it is to go overburden. 100 feet of number 12 has a certain amount of burden. Yes, it is. First of all, Matt, it is fairly easy to go overburden, especially with the length of the cable. And yes, you can actually do the calculations. If you need some help with that, we'd be happy to do that offline. But yes, you can absolutely and should absolutely calculate the theoretical burden that you have just based on the size wire that you have and the length of wire that you have. That is very possible. You can also add in the number of connections. Scroll up in your chat. Oh, and they're telling me I may have missed one. Hold on. If an engineer designs a service transformer at 150 kVA and specs a CT at 400 to 5, what do most techs do to recommend proper CT size? So you're saying if they haven't spec'd the correct CT size, how do you come back to that engineer and let them know that maybe he wasn't right about that? Well, one way that you can do it is, once again, extended range transformers gives us an opportunity to open a new dialogue and say, oh, by the way, you know, the new extended range transformers may operate in this range, or you pull out the operating specs for that transformer and you demonstrate and you show them, hey, is this the right one or should we go with something? I've got some smaller ones at the shop that I'd like to use and I was just checking it out. Don't tell him he's wrong, but show him that the smaller ones actually work a little bit better with their thermal rating factor. So again, and it may be that you weren't aware of something. It may be that this particular site is expected to increase dramatically in 2 years, or this is the first stage of an installation. So there could be more information that the engineer has that you may not have. So don't get all uppity on him and let him know that he's making a real mistake. Maybe he is, maybe he's not. Again, be sensitive to the fact that anybody who's not from metering can very easily make a metering mistake because you just don't learn about this stuff until you've been doing it. And that's the sad truth. All right, and let me see if I missed any other. How often do we recommend testing them? Less inventory. Okay, I think bar if possible, less losses. Bar if possible, less losses in an inductive window. That's true. The bar types do only go up to about 800 amps. I've never, the really large services, I've only seen the donuts, so you don't have a choice. However, if you're putting in, I don't know how many of you use 2000 to 5s, 4000 to 5s. If you are putting in a large transformer, spend the time to put that cable as best you can, have that cable go right through the center of that service. Not so problematic at 2000 to 5. It really starts to show up once you get to 4, 5, and 6000 to 5. So if, and only if, most utilities, they're not doing it that way. But if you're using those and they are out there, make sure that you take the time to put those cables through the center of the services. So thank you for that, Jim. And I think that I am 3 minutes over. I apologize. And I will let you guys escape. So happy Halloween, everybody. And we will see you guys all next Tuesday, election date here in the States. Should be an interesting day. We're looking forward to it. Oh, and we've got for next week, it's going to be, as I've mentioned several times now, ratio burden and admittance. And then we're doing one on lessons learned from AMI deployments for asset management, harmonics, complete site testing, which was a question that was asked earlier, electric vehicle trends and calibration, and then streetlights and 5G metering and testing. So we've got a few more. Again, this is really supposed to mimic a meter school. So hopefully it's been fun. If you have any questions, concerns, if you like what we're doing, tell us. If there's something more that we didn't do or could improve, tell us that too. All right. Thank y'all. Happy Halloween, everybody.